In this video, we're going to start talking about physical properties and their relationship to intermolecular forces. So the first one is going to be boiling point. And I talked a little bit about that in the last video when we were talking about the strength of London dispersion forces, and I had compared fluorine to bromine to iodine, and we said that when we're going from a liquid to a gas, we're breaking intermolecular forces, right? We're breaking connections between particles. So when a substance boils, what we need to do is overcome those intermolecular forces. The stronger the intermolecular forces, the more energy we need to break them, so the higher our boiling point. So boiling point, we have a liquid going to a gas, and actually the point at which something boils is actually in equilibrium. So gas does go back to a liquid at that point. So our boiling point, and we could say our condensation point, are actually the same temperature. We are going to look at the process of going from a liquid to a gas, so I'm going to look at it in that direction, but again, technically it is an equilibrium. So when we're going from a liquid to a gas, we're breaking connections, so we need to overcome our intermolecular forces, right? Liquids have intermolecular forces between particles, while gases do not. So when we're going from a liquid to a gas, we're breaking those connections. The stronger the intermolecular forces, the more energy is needed to break them. And just remember, temperature is our average kinetic energy. So the more temperature we need, the higher our temperature. So higher boiling point. Right? Boiling point being that temperature where our liquid's going to a gas. So if we were comparing London dispersion forces, right? So if we were comparing different molecules, one that has just London dispersion forces, one that also has dipole-dipole forces, and then another that also has hydrogen bonds. As we go in this direction, our intermolecular forces are getting stronger, so we're going to have higher boiling points. An example, if I was to compare diatomic chlorine to this aldehyde, right? I have a carbonyl bonded to a hydrogen, to this alcohol. So chlorine is nonpolar, right? It only has London dispersion forces. My aldehyde is polar, right? This oxygen is more electronegative than that carbon, so I do have a dipole going in that direction. So dipole-dipole interactions. Also London dispersion forces. There are lone pairs on that oxygen. Let me stick them in there. So I do have an oxygen with a lone pair, but I don't have a hydrogen bonded to it. So remember, to have hydrogen bonds, which my alcohol here has, I have to have those lone pairs on oxygen, but also a hydrogen bonded to it. Right? In the aldehyde, I have a hydrogen, but it's bonded to carbon, not oxygen. So be careful, be able to recognize those. So this one does have hydrogen bonds. It also has dipole-dipole interactions. If it has hydrogen bonds, it is generally also going to be polar. So it will also have dipole-dipole, and then, of course, it has electrons, so London dispersion forces. So as we go in this direction, these are going to have a higher boiling point. If you have molecules that have the same functional group, So if we were to compare one alcohol to another alcohol or one aldehyde to another aldehyde, so molecules with the same functional group, more surface area, generally means a higher boiling point. Remember, our London dispersion forces are going to be higher if we have more surface area. So comparing one alkane to another alkane. We could also say more polarizable atoms, generally a higher boiling point. Remember, polarizable, we talked about this briefly in a previous video. It means that it has a lot of electrons, it's big, right? Lots of electron shells, energy shells, and it can stabilize those electrons. It also can have induced dipoles pretty easily because it is kind of big and floppy, right? Remember, as electrons get further from the nucleus, they're not held as tightly, right? Because they're further from the positive charge. So they're easy to distort also. Melting point is our next one. And melting point is going to be our temperature, or sorry, our point, right, temperature, where a liquid is going to, sorry, a solid is going to a liquid, but as with boiling point, it is actually an equilibrium point. So the liquid is going back to a solid. So my freezing point, liquid to solid, and my melting point, solid to liquid, would actually be the same temperature. Because we're using the word melting instead of the word freezing, I am talking about the process of going from a solid to a liquid. And just like with going from a liquid to a gas, we're breaking intermolecular forces. So we need to overcome intermolecular forces. In solids, all of the neighboring particles have good connections to each other. In liquids, I have some connections, but not as many as I do in a solid. So we are breaking intermolecular forces when our substance melts. And in general, stronger intermolecular forces are also going to be a higher melting point. That's supposed to be an E and an R. Not that you can tell. Stronger intermolecular forces, right? Harder to break. So higher MP, melting point. This last little part that I'm about to add is where it gets a little confusing because this is going to be different than we had with our boiling point. So with the same functional group, so for molecules with the same functional group, more symmetrical molecules have higher melting points. So arrow going up meaning higher. So for molecules with the same functional group, the more symmetrical the molecule, the higher the melting point. Be careful, this is different than we did with boiling. So same functional group, the more surface area, generally the higher the boiling point. With melting point, same functional group, the more symmetrical, generally the higher the boiling point. So an example of what I'm talking about here. If I was to compare these two, So these are isomers of each other. They're both C5H12. The melting point of my first one here is a negative, and actually let's add one more, sorry. I know it's annoying when I change it on you, then you have to like scribble out your notes. I'm gonna add this one too. So it's also gonna be an isomer, C5H12, if you wanna count your hydrogens on there. They're saturated hydrocarbons. These guys are all alkanes. And let's actually do our boiling points first. So using our trend, I'm going to expect my first one here is the one with more surface area to have the higher boiling point. And it is, I'm looking up the numbers here, 36.1 degrees Celsius. I would expect this one in the middle to be next, and I have 27.8 degrees Celsius. And then this last one, which has less surface area, has the lower boiling point of 9.5 degrees Celsius. So those are the temperatures at which they would boil. If I look at the melting points for these, however, the one on the right is my more symmetrical molecule. So that one actually has the higher melting point. So the melting point for this one, a negative 17 degrees Celsius. The one in the middle, a negative 160 degrees Celsius. And the first one, a negative 129.8 degrees Celsius. So these all have the same functional group. They're all alkanes. Using what we had learned about London dispersion forces, right? We said the more surface area, the stronger the London dispersion forces. So that trend makes sense when I look at my boiling point, right? My first one, where it's just all 5 carbons in a straight chain, has more surface area than the one in the middle, which has more surface area than the one on the end. So those numbers make sense. When I look at my melting point, though, they don't necessarily follow that trend. So my lowest or my highest melting point, keep in mind these are negative, so negative 17 is my highest number here, is for the one that has the 2 branches on it, my more symmetrical one. And then my second one is over here, which is more symmetrical than this one in the middle, right? The one in the middle isn't as symmetrical as the 2 on the ends. The reason for that has to do with how they pack together. So for our melting point, symmetrical molecules pack together better. Meaning they can kind of get closer to each other. If I was to try to stack them close, right? Because remember, intermolecular forces are between particles. So it's easier to draw with this one. If I was to take that one and try to get another one close, I can kind of lay them on top of each other. So when I'm forming those temporary dipoles, because they can get close together, they tend to be pretty strong. If you have something that's unsymmetrical, right, I can only get these so close, even if I put them in the same direction, because of those like weird bonds and things, or the branches. So the more symmetrical it is, the easier it is to pack it together. The better you can pack them together, the closer they are to each other, and the stronger those connections are. So they can just get closer to each other if it's more symmetrical. Remember, solids, the particles are close, and this goes back to like your 130 days again. In solids, the particles are really close to each other. Liquids, not so much, because I've broken some of those connections, and then in gases, they're really far apart. So for melting point, if it's symmetrical, they pack together better. So the connections are stronger. So So again, going back up and looking at these numbers, right, the one that has the lowest melting point, the lowest boiling point is my one that has the highest melting point. So the trends are different. So just do be careful if you're doing a quiz question or any sort of question and I give you these and ask you to rank them according to boiling point or melting point, those rankings are going to be different. So again, just go back up and pay particular attention to this part. So same functional group, more symmetrical, higher melting point. Same functional group, more surface area, higher boiling point. The next property we're going to talk about is solubility. And solubility has to do with the extent to which a solute will dissolve in a solvent. So remember solutions. Solutions were types of homogeneous mixtures, right? There's two types of mixtures, homogeneous and then heterogeneous. Homogeneous mixtures were mixtures that don't look like a mixture, right? They have a uniform composition. So if I was to make Kool-Aid, right, I'd take sugar and I would take Kool-Aid powder and I'd take water and I'd mix it all together. And when I'm done, it looks like one thing, right? It's homogeneous. So Kool-Aid would be an example of a solution. Heterogeneous mixtures are mixtures that look like mixtures. If you take two things and you mix them together and it's obvious that there's more than one type of thing in there, it is heterogeneous. So solutions, a type of homogeneous mixture. And then remember, solutions are made up of two types of components, solutes and solvents. The solute is the component or components. You could have more than one solute that's present in the smaller amount. My solvent was the one present in the larger amount. So in that Kool-Aid example, Kool-Aid powder and sugar are both solutes. Water is my solvent. So when we're talking about the solubility, we're essentially saying how much solute will dissolve in that solvent. If a lot of it will dissolve, I would say it has a high solubility. If it not much dissolves, then it has a low solubility. And this is where that like dissolves like, also going back to our 130 days. So our like dissolves like statement comes into play, right? This is the one that says that polar things will dissolve in polar things and non-polar things will dissolve in non-polar things, and polar and non-polar things will not form a solution. They could form a heterogeneous mixture, but not a homogeneous mixture. So polar solutes tend to dissolve in non-polar, polar solutes tend to dissolve in polar solvents, like they're both polar. Non-polar solutes tend to dissolve in non-polar solvents, and we could say that polar and non-polar substances will not form solutions. They can still form a mixture, it just won't be homogeneous. It doesn't matter, instead of using the word solute and solvent on this one, I worded it differently because I didn't want to have to say it twice, because it doesn't matter which one's the polar one and which one's the non-polar one, right? So you could say polar solutes will not dissolve in non-polar solvents, or you could say non-polar solutes will not dissolve in polar solvents. So I just worded it differently so we don't need to write it twice. But like dissolves like. If it's polar, it'll dissolve in something that's polar. If it's nonpolar, it'll dissolve in something that's nonpolar. If their polarities are different, they will not form solutions. So depending on what our functional group is, it may or may not be polar in water, right? Water is a common solvent, but water is a polar molecule, right? Water has a bent shape. I have my two lone pairs, but that's not what makes it polar. What makes it polar is the fact that oxygen, right, is more electronegative than those hydrogens. And then because the shape is bent, right, if it was linear, it would be nonpolar. But because that shape is bent, it's a polar substance. In general chemistry, water was our most common solvent because we dealt with a lot of ionic substances, and ionic substances are just polar by definition, right? I have a positive end and a negative end, so it's definitely polar. So things that are polar will dissolve in water. You did have to use our solubility rules. There were some exceptions there, right? Things that are insoluble, which you then learned in 152. They're still slightly soluble, right? All that KSP business. But in general, organic molecules don't always dissolve in water, right? If we were to look out at alkanes, alkanes are nonpolar, right? They only have carbon and hydrogen. Carbon-carbon bonds are definitely nonpolar because the electronegativity of carbon is the same as the electronegativity of carbon. Carbon-hydrogen bonds do have a small electronegativity difference, but it's below that threshold, so we consider them nonpolar. So an alkane is not going to dissolve in water, right? Alkenes aren't polar, they're not going to dissolve in water. So often in organic, water is not going to be our solvent. We have to use more organic, more non-polar solvents, right? Water. This guy here, strongly polar. So some common organic solvents. And this is by no means a complete list. I just want you to kind of start getting used to seeing some of the things that we're going to be using as solvents. So carbon tetrachloride, CCl4, right? So sp3 hybridized carbon, but instead of bonded to 4 hydrogens, I have it bonded to 4 chlorines. Carbon tetrachloride, that's nomenclature that you would have learned in 150 or 130, right? It's got covalent bonds, so you use those prefixes. So 1 carbon, 4 chlorines, and then the last part of chlorine becomes chloride. So carbon tetrachloride. Hexane is another common one. We're going to learn to name molecules pretty soon, but hexane is just a straight chain alkane with 6 carbons. 1, 2, 3, 4, 5, 6. So hex is our prefix for 6. Ane, because it's an alkane. So that's just what hexane looks like. We could draw, if we wanted to be consistent, we could draw a carbon tetrachloride. One coming out, one going back. You'll see diethyl ether a lot. A lot of times they'll just call it ether. Ether is an entire functional group though, so that's just kind of being lazy. The one I'm going to draw is actually diethyl ether. Remember, ether was that functional group where I have a carbon-oxygen-carbon bond. So that's what that one would look like. And there's others. These are just some of the more common ones. We'll add to our list of solvents as we go on. In Chapter 7, we're going to look at a lot of different types of solvents. So kind of back to water. As a general rule, because if I was to look at, I know I'm jumping around, sorry guys. If I was to look at this alcohol, right, I would expect this to dissolve in water. It has similar intermolecular forces, right? The intermolecular forces need to be similar because then I know my polarity is similar. So this can form hydrogen bonds, water can form hydrogen bonds. So this actually would be a little bit water soluble. However, if I go and add more carbons to this, what happens is that this entire part is nonpolar. And it's just this little bit, that's supposed to be a bracket, sorry, that's horrible, is polar. So looking at an organic molecule, just because it has a polar end, doesn't mean it's necessarily going to dissolve in water. If your non-polar portion is actually bigger than your polar portion, then the net effect of that molecule is that it's not going to dissolve in water. So you really have to kind of look at the entire molecule, not just the functional group when we're looking at water solubility. So as a general rule, which is what I was going to write by that asterisk before I didn't give myself enough room, as a general rule, an organic molecule will be water soluble if it contains a polar functional group that can hydrogen bond with water for every 5 carbons. And it's about 5 carbons, but we'll use 5 as our cutoff. There is a little bit of fuzzy, gray area on both sides of that, but we'll stick with 5. So as a general rule, an organic molecule will be water soluble if it contains a functional group that can hydrogen bond with water for every 5 carbons. So if you have one group that can hydrogen bond with water, and then you have more than 5 carbons, it's not going to be water soluble. If you have a functional group that can hydrogen bond with water, and then you have 5 or less carbons, it can dissolve in water. So if we go back and look at this one, and then I'm going to draw the original one that I drew. So I have one group in each that can hydrogen bond with water. And then if I count my number of carbons in this one, 1, 2, 3, 4, 5, 6. I have 6 carbons. If I look at this one, 1, 2, 3, I have 3 carbons. So this one has one group that can hydrogen bond with water for every 3 carbons. So this one will be water soluble. For the one on the left, I have one group that can hydrogen bond with water for every 6 carbons. So this one is not water soluble. If I put this one in water, it will not form a homogeneous mixture. A couple more examples. We're going to determine if the following molecules are soluble or insoluble in water. So I'm going to draw a few examples for us. So I have a chlorine on there. I have a ketone functional group. Let's actually do another ketone. Oops. A carboxylic acid. And let's do an ether also. I'm going to do an unsymmetrical kind of big ether. Okay, so what I want you to do is do that pause thing again. I would like you to try these on your own. So we're looking at them and we're saying, can it form a hydrogen bond with water? Now be careful, I'm not saying a hydrogen bond with itself, but with water. And then if it can, does it have, for every group that can do that, does it have 5 or less carbons? So please give it a pause, and then when you're ready, come on back. Okay, hopefully you guys did that one. So this one, it cannot hydrogen bond with water, my one with chlorine on it. It's a polar molecule. I have dipole-dipole forces. I have lone pairs on chlorine, but remember I need an oxygen with a lone pair, nitrogen or fluorine. So this one, no hydrogen bonds at all. So this is going to be insoluble in water. Because it's polar, it would actually be slightly soluble, but we're going to consider it just insoluble. My ketone, we're going to this one here, not the one below it. I'm going to do this one first. So this one, and this was why I wanted to add this, this can hydrogen bond to water. It can't hydrogen bond with itself, right? If I had one ketone trying to hydrogen bond with another ketone, it can't. Oxygen has lone pairs on it, but remember the second half of our criteria is we had to have a hydrogen bonded to oxygen, and I don't in that ketone. I have hydrogens bonded to carbons, but I don't have hydrogen bonded to oxygen. So ketones cannot form hydrogen bonds to themselves. So if we were talking about melting point and boiling point, I would only give it London dispersion forces and dipole-dipole forces. It would not have hydrogen bonds. But water can supply that hydrogen, right? Water has a hydrogen bonded to oxygen. My ketone has a lone pair on oxygen, so we actually meet that criteria. So while a ketone cannot hydrogen bond to itself, it can hydrogen bond to water. So I do have a group that can hydrogen bond to water. I have 4 carbons, 1, 2, 3, 4. So this one is actually going to be water soluble. That one might have been a little bit tricky if you didn't see the whole hydrogen bonding to water part. This other one, the same sort of idea, my other ketone, it can hydrogen bond to water because water can supply that hydrogen that's bonded to oxygen. So it can do that. But I have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. So we needed to be 5 or less. So this one is going to be water insoluble. Right? Not going to form a solution with water. Looking at my carboxylic acids, let's draw this one out too, can actually form 2 hydrogen bonds with water per molecule. So I have lone pairs on oxygen there and a hydrogen. Carboxylic acids can hydrogen bond to themselves because of this hydrogen. And then I also have lone pairs on that oxygen. So that one can hydrogen bond to the hydrogen of water. So for each carboxylic acid, there's actually 2 possible intermolecular forces with water. This hydroxyl part, I can either hydrogen bond it that way, right? I can use the hydrogen on my hydroxyl group to form the connection with a lone pair on water's oxygen. Or if I wanted, I wouldn't do both, so let's erase this one. I could also do this. It's not that it can't do both, it just gets crowded. Remember all of these things, I don't have O's and H's floating around, right? I have charge, right? I have a nucleus and then I have electrons. And if you try to get too many electrons in one spot, they're just gonna repel each other. So it just becomes too crowded to try to do both, but we can do that. So carboxylic acids, again, can form 2 hydrogens per water per functional group. If I was to put 2 carboxylic acids on the same molecule, I can now form 4 for that molecule. So this one's definitely water soluble, right? I have 2 groups. I have 1, 2, 3, 4 carbons, so water soluble. I could go up to 10 carbons on this one and it would still be water soluble, right? If I did, I'm not counting, I should have counted. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That was lucky actually. So I have 10 carbons. I have 2 groups, right? It's 1 functional group, but 2 parts I can hydrogen bond with water. So this one would be water soluble. So watch out for those carboxylic acids. Okay, my ether. Ether's like my ketone, right? I have a lone pair on that oxygen. I have a hydrogen attached to oxygen on water, so these can form hydrogen bonds. However, I have 1, 2, 3, 4, 5, 6, 7, 8 carbons, so that's too many. So water insoluble. Right? If I had a smaller ether, if I did diethyl ether, this one is actually going to be slightly water soluble. Remember I said there was some gray area around that 5. So when I get to 4, it's not super water soluble, but I would still consider it water soluble. Again, it's slightly. That's supposed to say slightly.